All right, these are your first notes for the week. This is still continuing in chapter 13, 13-4, compound probability. It's in your book. Remember, we're in the second volume, page 865. Your paper should be set up like this for notes because we did this warm up in class, or we will have done this warm up in class. But your essential question for today is, how do I identify independent and dependent events and find compound probabilities? Okay, so as we go through this lesson, try to keep that in mind, that that's what this is about. So here we go. We have a little bit of vocab. So go ahead and pause if you need to, and then copy these down. There, it's a little better zoomed in. Okay, so we'll just, well, I'll let you see all of them. So a compound event is an event that is made up of two or more events. So we've done simple probability, which is just one event, like one thing could be just flipping the coin and what's the probability of heads. That's one event. Another thing could be you have a bag of tiles with letters on them, like how we've had, and what is the probability of drawing like an A? So those are independent, or those are just single events. A compound event would be two or more events, like flipping a coin and then drawing a little letter tile out of a bag, or maybe drawing a card out of a deck of cards, or maybe rolling a dice. So it could be two or three or more events, but like different kind of things. Okay. Independent events are when one event does not affect how another event occurs. So in my mind, I think of them as separate. What happens in one event, one thing, it's not going to matter when you're thinking of the next one. So it's like rolling a dice and then flipping a coin. They're completely separate. It doesn't matter what number I get when I roll the dice, it won't influence or have any effect on flipping a coin and getting heads or tails. So independent means separate. They don't have anything to do with each other, and they won't affect it. They won't affect probability. All right. Dependent events are when one event does affect how another event occurs. So one thing will then affect how the outcome is of the next event. So it's like picking a colored marble out of a bag. So like imagine there's 10 marbles and whatever the colors are, but you pick one and you don't put it back, you're keeping it. So if there were 10 marbles, then you keep one, now there's only 9 marbles. So that would affect when you then pick another marble. If you picked one and then put it back in the bag and then picked another one, that wouldn't have an effect. That would be independent. But a dependent event, it means that one thing happens and then that does have an impact on the next event occurring. You'll understand it more when we get into some examples. All right, so go ahead and write this down. We're going to go to the book real quick and do some examples. If you don't have the book, you can just write it in the notes. You don't have to write the problem, but just maybe write down the work. So examples in the book, page 865 to 869. All right, so we're going to start with this first problem. This is page 865. So just follow along with me. So we're going to start with identifying independent and dependent events. And remember, pause whenever you need to. If you need to go grab your book or whatever, just pause the video. Okay, so you roll a standard number cube, that's a dice. Then you flip a coin. So rolling the dice, does that have any effect on then flipping a coin and getting heads or tails? I can't draw a coin, but would that have any effect on it? Would it be independent or dependent? And explain. So this would be independent. I would just say these events don't affect each other. So it is independent. It's independent. Okay. So these events don't affect each other, so it's independent. It doesn't matter what I get when I roll the cube. I might get a 1. It's not going to have any impact on flipping the coin. Okay. Let's do some more examples. So the more we do it, the more it'll make sense. So now I'm at the top of page 866. I'm just going to continue on with these kind of problems. So again, this is the top of page 866. So it says determine whether the outcomes of each trial are independent or dependent events. And again, we're just thinking back to the definitions. Independent events are when one event does not affect how another event occurs. Dependent events are when one event does affect how another event occurs. So it all has to do with having an effect on how the next event occurs. If it does have an effect, it's dependent. All right. So it says for number 1, a card is randomly chosen from a standard deck of cards, then replaced. Another card is chosen at random. So replaced means, write this down too, it means put back. If you take the card but then put it back, if you think about it, it's not going to have any impact on the next card chosen at random. So if you think about it, it's kind of like two completely separate things. It's independent. Okay, now the next one, it says asking a student's age and then asking what year he or she expects to graduate. So for one event, it's asking a student how old they are. So, whatever the answer is, let's just say maybe they're 16, just to get our minds thinking about this. And then if you're asking what year he or she expects to graduate, does that have, or does the age, so here's the question, I'll actually write it. Does age affect, because that's what it's all about, does age affect graduation years? So I want you to think about that. I would say it does, especially in high school. If you're a certain age, you can predict when, or like not predict, but you can tell when they'll graduate. But if you, I don't know what I was going to say. So anyways, it does affect. So that would be dependent. Dependent. Whoops. Okay. Dependent. All right. And then just real quick, I wanted to go back to this one and kind of explain it again because there's no other examples like it. So if someone did choose a card from a deck of cards, but then did not replace it, if it said they kept the card, and then another card is chosen at random, whatever card that person picked, now it's not going to be in the deck of cards for the next one. So whatever that card is, they can't pick it. And out of the total, think about it, the total has changed also. So that does definitely, it would have an effect if someone kept a card. So what I want to do real quick is go back to the notes. And I want to just add one little note. If you see the word replaced, that would be independent. Whoops, let me zoom that out a little. Okay, so if you see the word replaced, it would be an independent event, but for a dependent, it would be not replaced. And that could be, a deck of cards, or it could be picking a marble out of a bag, or a lettered tile, like how we've done those kind of problems. If they keep it and they don't replace it, not replaced, it's dependent. If they do put it back, it's like it resets it back to normal and it's independent. Okay, so we're going to do a couple more examples out of the book, but real quick, let's add a little more to the notes. This is for the next part. Let me zoom that in again for you. There we go. So pause it if you need to. I'll just start explaining this. This is probability of A and B. And this follows along in the book too, so you can see it in the book. I'll show you in a second. So probability of A and B. So if you say the probability of something and something else, A is one event and B is another separate thing. So two events A and B are called independent, like up above. They're independent if and only if probability of A and B equals if you know they're separate probabilities. So probability of event A occurring, and then you multiply it times probability of event B occurring. So for example, what did I say up here? Rolling a dice. Let's say the probability of rolling a 1 on a dice, that's 1 out of 6, 1/6. And then flipping a coin and getting heads, for example, is 1/2. So you would take your 1/6 and multiply it times 1/2. And that's how you find probability of A and B. You just multiply their separate probabilities. And then you can use this to also test for independence. So if you know probability of A and B, if they give you a number, and then you know there's separate probabilities, you can test for independence to see if this is actually true. I think there is some examples like that too in the book. We'll go to those in a second. All right, so this is in your book. This is page 866 again. So we are just on this page. So this is what you just took notes on. So two events A and B are independent if and only if probability of A and B equals probability of A times probability of B. So first we're going to find the probability of independent events just like what it says up here. So this is what we're going to use. But then on the next page, we will test for independence, which is pretty easy once you understand how this whole equation works. All right, so let's look at problem 2. Okay, so you roll a standard number cube and spin the spinner at the right. So it's like saying event A is rolling the standard number cube and event B is the spinner at the right. So that's like every time you're seeing A and B, that's what it means. There's one event and then another separate event. So what is the probability that you roll a number less than 3 and the spinner lands on a vowel? The key word here is the and. Later on, we'll see there's another word that could be. So and, see how it says and? So I know that it's going to be multiply. I multiply the two events together. So probability of A, since I did an A up here, I'm going to look at that. So the, again, it's right here. Roll a number less than 3. So I have to think of numbers less than 3. There's 1, 2, 3, 4, 5, and 6. Which ones are less than 3? Not less than or equal to, just less than 3. There's only 1 and 2. So that's 2 out of 6. And you can reduce it or not. You're going to multiply it anyways, so it won't really matter. So I'll just leave it as 2 out of 6 because I know most of you probably don't want to reduce that. Okay, probability of B is the spinner lands on a vowel. So I have to look at this little spinner and see how many vowels are there. There's V, X, W, and U. So there is only 1 out of 4. And then probability of A and B would be 2/6 times 1/4. You can use your calculator on your Chromebook, on your phone. I'm just going to show on this one. So I would do 2 divided by 6 for 2/6 times 1 divided by 4. And that is hopefully correct. And I'm going to round it. So I'm going to put my approximately equal to 0.083, and it repeats. So you can multiply it in the calculator and get a decimal. I forgot you can also multiply fractions straight across, of course. And I would want to actually reduce it. So that would be 1/3. And if I multiply straight across, it would be 1/12. And I can check my answer to see if these are actually equivalent by doing 1 divided by 12, and it should equal the same thing, and it does. So you can write your answer either way. You can even write it, remember, as a percentage. So I'd move my decimal 2 times to the right, 8.3, and it repeats percent. So all 3 of those are the same thing, 1/12 or 0.083 or 8.3%. It doesn't tell you which way to write it, and I forgot what MathExcel tells you. It probably says reduced fraction, maybe an integer, or I don't know what it says. So just pay attention to what MathExcel asks you for. All right, we'll do one more. We'll do this one. So you spin the spinner at the right, and without looking, you choose a tile from a set of tiles numbered from 1 to 10. Find each probability. So it says each probability because there's a number 3 here and there's a 4 on the next page. So just find the probability of what it says here for number 3. So it's like saying find the probability that a spinner lands on an odd number, that's event A, and you choose an even number. The tiles are numbered from 1 to 10, so count how many even numbers are there. There's 2, 4, 6, 8, and 10. So 1, 2, 3, 4, 5. So that can help you to get the even number. So that would be event B. So probability of A and B equals probability of event A times probability of event B. And then I just have to find each separate one. So that would be for the odd number, I'm going to look over here. I see 2 odd numbers, 1 and 3. So 2 out of 1, 2, 3, 4. 2 out of 4 total numbers. You could reduce it to 1/2 if you want to. And then probability of event B, even numbers from 1 to 10. So there are 1, 2, 3, 4, 5, 5 out of 10. And actually both of those reduce to 1/2. So that's pretty easy to just reduce them both to 1/2 and multiply straight across and get 1/4. You can divide it in a calculator, or maybe you know that that is 0.25, or you could change that to be a percentage and it's 25%. Okay. All right, so next is we are going to test for independence. It says you can use this relationship where probability of A and B occurring is multiplying the separate probabilities together to test 2 events for independence. And remember, independence means that one event doesn't have an impact on the other. They're completely separate. Okay, so it seems a little blurry. Okay, the probability that event A occurs is 0.3, and the probability that event B occurs is 0.1. There is a 25% chance that events A and B occur together. Are events A and B independent? So what I'd have to do is see if 0.3 times 0.1 equals 25%, and remember that would be 0.25, and I'm going to do a question mark. So we have to test it. So I'm going to take my calculator and check and see. So I have to do 0.3 times 0.1. Oh, that doesn't equal 0.25. It's 0.03. Does not equal 0.25. Okay, so what I would say is no, A and B are not independent because 0.03 does not equal 0.25. Probability of A and B, it should equal probability of A times probability of B. And it didn't. Sorry, I didn't realize that wasn't showing. There. Okay, so we'll just do one more example. We'll do number 5 just to make sure you get it. So it says use the given probabilities to determine whether events A and B are independent. So here's event A, event B. Probability of A and B is 0.12. So I'm going to check it. I'm going to do 0.3 times 0.4. And I'm going to check. I'm going to see, does it equal 0.12? I know 3 times 4 is 12, so I'm thinking it probably does, but I'm going to use the calculator because I always want to make sure that I'm doing it right. So in my calculator, I just have to do 0.3 times 0.4. You try it too. And it does equal 0.12. So I would say yes, A and B are independent. And just looking ahead to the next one, you would just do 2/3 times 4/5. And I'm checking to see, does that equal 8/15? Think about just multiplying straight across. Would that equal it? 2 times 4 is 8. 3 times 5, 15. Yeah, it does equal 8/15 equals 8/15. Yes, independent. There. Okay, so remember, the way to test for independence, if you get a question, are these events independent? You multiply the separate probabilities and you see if it does equal probability of A and B when they give it to you. All right, so back to the notes, just a little bit more notes and then a little bit more examples in the book. So now I was telling you guys those previous problems said and. Now I'm going to show you if it says or what to do. So this is on page 868. These are called mutually exclusive events, and they can't happen at the same time. So if two events happening saying that so like for example, if I was rolling a dice and I wanted to say, what's the probability of rolling a 1 and rolling a 2 at the same time? It can't happen. So it's 0. Probability of A and B would be 0. They can never happen at the same time. Or like drawing a tile out of a bag with they have letters on them. And that one tile, I could say, what's the probability of it being an A, like the letter A, and a consonant? No, yeah, A is a vowel, so it's not a consonant. So that would be impossible, not happening. But what you could say is or. So if I said, what's the probability of rolling a dice and getting a 1 or a 2, for example? It could be a 1 or a 2. That could happen. Or picking a tile out of a lettered tile out of a bag of tiles, I could say, what is the probability of getting an A or a consonant? So there's a bunch of consonants, or it could be an A. So or works for those kind of events that can't happen at the same time. And you would solve it, you would calculate it by adding. So what I want to say is or add probabilities, I guess. Add probabilities. Because right here it says to add. Okay, so see how I'm writing in my notes and stuff and using color. Make sure you guys do that. It helps you to learn it a little bit better. And we'll come back to that last part. Okay, so now we'll do some examples in the book. And I already wrote in it a little bit, so don't mind my writing. So here's a little bit of notes that you can read through, a little bit of information. This is page 868, like I said. Okay, so page 868. So it says events that cannot happen at the same time are called mutually exclusive events. Feel free to read it on your own as well. And then this is the part we just wrote in the notes. You cannot have them happen at the same time. So you can't say and. But if you say or, you just add up the probabilities. And also it's called, well, the next thing we're going to learn about is called overlapping. These ones have no overlapping. So if you think about a Venn diagram, there is nothing that's in common for both of them. They're completely separate, exclusive events. Okay, so let's take a look at this problem. Let me turn that down a little bit. That's a little bit better. Okay, so it says a student athlete may participate in only one sport per season. In the spring season, 15% of the athletes play baseball and 23% are on the track team. What is the probability of an athlete either playing baseball or being on the track team? So notice that if it said and, they can't be playing baseball and on the track team because it's the school's rule that they have to only be in one sport per season. So anyways, I already wrote that it's the key word here. The important word to notice is or, which means you need to add. You add the separate probabilities. Sometimes you have to calculate it, but in this case, they just gave it to you. We're not always seeing percentages as or probabilities as a percent, but we can. So so the probability of being on baseball or track, I already wrote out probability of baseball. That's a plus. So see, it's adding plus probability of a student being on track. And if it's percentages, you can really just add them. So the percentage of baseball was 15. The percentage of track was 23. So just 15% plus 23%. Okay, so add those up, and that would be 38. 38. And that's really all you have to do. So just add the separate probabilities. So on the next one, though, we do have to calculate the separate probabilities. So it says a bag contains 3 blue chips, and a chip, I'm thinking of like a poker chip. I don't know what other kind of chip. It's not chips that you eat, because that would be really weird. So anyways, a bag contains 3 blue chips, 6 black chips, 2 green chips, and 4 red chips. Like just little round things. So there's like 4 red. So since I have a red, I'll show the 4. I'm not going to show all of them, but I was thinking I do have a blue also. So just imagine like little plasticky round things that are different colors. Okay. So number 7 says the probability of a green chip or a red chip. And think about it. If it said and instead, so if it said probability of a green chip and a red chip, and you're only picking one, that's impossible. There are no green and red chips. There's either green or red or blue or black. So anyways, it says or, so you add. So I already wrote this out. You can write it down. Probability of green plus probability of red. So in order to find the probability, we need to know the total. So I have 3 plus 6 plus 2 plus 4. So 9 and 6, so 15. So whatever the green is, it's out of 15. Whatever the red is, it's out of 15. So I have to just look back. Green, there's 2. And red, there's 4. Remember, when you add fractions, you need to have a common denominator. So luckily, we do have a common denominator. Just add the top numbers. 2 plus 4 is 6 out of 15. And you can also use a calculator, but you don't need to. Adding these is pretty easy. So I just want to make sure I have my answer. 6 out of 15. If you could reduce it, you would, but we can't. All right, so here's the other one. For this imagine the same colors of chips in the bag. So what's the probability of a blue, black, or red? So you would do probability blue plus probability black plus probability red. So from above, I already know red, which is 4. So 4 out of 15. Then I just have to look back at the problem. Probability of blue, there's 3 blue chips, so 3 out of 15. The black, there's 6. 6 out of 15. And just add all of those up since it says or. Whenever you see or, add. So since they all have the common denominator of 15, I know my answer will have a 15 on the bottom, and I have to just add the top numbers. 6 plus 4 is 10, plus 3 is 13. So 13 out of 15. Pretty likely that you would get blue or black or red. The only other color is green, and there's only 2 of them, so it makes sense. A probability that would be over 1 wouldn't make sense. So if I maybe got 17 out of 15, I would know I must have added wrong or something, or maybe I wrote a number wrong. So just always think about it, does it make sense? All right, so real quick, there's one more thing to learn about, which is called overlapping events. So add this into your notes. Pause if you need to. Oh, let me move that. Okay. So this is just on the next page over, page 869. Overlapping events have outcomes in common, like picking a card out of a deck of cards that is even or a heart. So there's some outcomes in common. So if I'm saying picking one card out of a deck of cards that is even or a heart, there are a lot of even cards. There's 2, 4, 6, 8. There are 10s. But after 10s, remember, it goes to Jack, Queen, King, Ace. So there's those ones that are even. And for every number, there's 4 suits. There's the heart, the spades, diamonds, and clubs. Okay. So anyways, there will be these even numbers will also be a heart one time. So there'll be 1, 2, 3, 4, 5. So they overlap with 5 cards. If you're counting all the even cards and then all the heart cards, there are these numbers, if they had a heart, that you would count twice. So what we have to do to account for that is subtract the ones that don't count one time. It looks like this in a formula, but it's also kind of common sense. So you might know to do that without really thinking about using a formula. So anyways, if they're overlapping events, probability of A or B, remember or means to add. The difference here is that you have to subtract the probabilities of A and B, even and a heart. So even and heart. So if they overlap, there's going to be something that overlaps. Remember that if A and B are independent events, probability of A and B would be if you multiply it together. The separate ones, multiply it together. And that's a way you could find that if it wasn't given to you. I know that sounds really confusing, but if you come across a problem where you don't have probability of A and B, just remember multiply those two together and that's what you would subtract. Okay, so let's do a couple examples. This is on page 869. Let me move some stuff around. So you can look through this if you get confused or if you want to try to understand it better, which you should hopefully. Read through this. It's pretty interesting and it helps you understand what we mean by like overlapping. It's the ones that they have in common in both events. Okay. But anyways, let's go ahead and do an example because these notes are getting kind of long. All right, so we're going to do this got it problem, finding probabilities of overlapping events. What is the probability of rolling either an odd number or a number less than 4 when rolling a standard number cube? So I'm going to find probability of odd or, let me write that down, odd or number less than, I'm going to use the symbol 4. So if I'm rolling a standard number cube, there's 1, 2, 3, 4, 5, and 6. And I'm going to show you using the formula of, let me just use a pen so it's smaller. I'm going to show you probability of odd plus probability of number less than 4. And then I'm going to subtract probability of odd and less than 4. So I'm going to find the separate probabilities and then the ones that say with the and, we're going to find that one. So probability of odd, how many odd numbers are there? There's 1, 2, 3. 3 out of 6, but I'm going to add the probability of numbers that are less than 4. So less than 4 would be 3, 2, 1, so that's 3. It's also 3 out of 6. But then I have to subtract if I look at these. All right, so the numbers that are odd and less than 4, there's 1 and 3. So that would be 2 out of 6. So I'm going to go ahead and calculate this. And then I'm also going to show you, like it shows right up here with the Venn diagram, just real quick. So 3 plus 3 minus 2, since they all have a common denominator, adding and subtracting fractions, you just go basically left to right. Look at the top numbers. 3 plus 3 is 6, minus 2 is 4. So I'm really just doing 3 plus 3 is 6, minus 2 is 4. And then I do want to reduce my answer, divide top and bottom by 2. So it's 2/3. So divide by 2 to the top and bottom. So I get 2/3. But real quick, I wanted to show you the Venn diagram of the numbers. So they do overlap in the middle. What do we have? Odd over here. And then number less than 4. That's my less than symbol. Okay, so I also have to draw the box. Anything that's not that, it'll be outside in the box. So my odd numbers would be my 1, 3, 5. But if it's also less than 4, I have to write it in the middle. So my 1 and 3 go in the middle, but my other odd number would be 5, and that goes there. And then numbers less than 4, well, yeah, I already have 1 and 3, but there's also 2. 2 would go here. All of the numbers that I didn't count, that don't satisfy odd or number less than 4, they go out here, which we call, this is like the universe. So I have my 1, 2, 3, and 5. So I have 4 and I have 6 out there. So now let's look at the fractions that we had and just kind of see how it relates to here. When I said odd numbers, there was 1, 2, 3. 3 out of 6 total. 1, 2, 3, 4, 5, 6. Yeah, we have 6 total numbers. And then numbers less than 4. Look at over here, number less than 4. There's 1, 2, 3. 3 out of 6. But then you subtract the overlapping part. I'll shade it in actually. Right here is where they overlap, which is right here. So it's all about that overlapping part. We can't count these twice. I can't count them as odd and then count them as less than 4. You can only count them one time. So that's why we have to subtract it away. But if you just used common sense, I know this is a big explanation, but if you're thinking of odd numbers or numbers that are less than 4, you can probably come up with them and think, okay, odd numbers or numbers less than 4, odds would be 1 and 3. And then also less than 4 would be 2. Oh, I forgot 5. So odds would be 1, 3, 5, and then numbers less than 4 would include 2 as well. And then you just count them up. There's 1, 2, 3, 4. 4 out of 6 for probability, and that's what we got. So again, you might be able to just figure this out with common sense. If not, find the separate probabilities, add them, subtract the overlapping part. Okay, so make sure you guys finish up your notes, and you'll have quite a bit that we actually wrote in the book for today. Get your 3 questions on the left in a summary, and also work on your Math Excel assignment.